Our next topic is rational numbers, which means we're about to start looking at fractions and mixed numbers and decimals. Now to look at how we got to where we are right now, we've talked about the integers as representing the whole numbers plus the opposites of the whole numbers. And we've looked at representing those integers on a number line, and we also said that even though we recognize that there are numbers in between those numbers, that we were going to pretend that nothing existed between the integers. But we know that numbers do exist between the integers. So some of the numbers that exist between the integers are called rational numbers. The definition of a rational number is that it's a number that can be written in the form a over b, where a and b are integers and b is not equal to 0. 2/3 is an example of a rational number. 2 is an integer and 3 is an integer. One really good website for exploring fractions is called visualfractions.com. You might want to check the site out. You'll be able to see what fractions mean. You'll be able to explore fraction operations like addition, subtraction, multiplication, and division, and you'll be able to compare fractions. Now, there's different ways to represent fractions, and we're going to use the fraction 2/3 as our example. One way is with an area model. Now, what's important with any representation of fractions is to know what is representing the whole. In this case, the rectangle is representing the whole. And to show 2/3, we have to take this rectangle and divide it into 3 equal parts. It's important when you're speaking of fractions that you talk about dividing the whole into equal parts. If we shade in 2 of those 3 equal parts, we can say that the shaded part represents 2/3 of the whole rectangle. So this is an example of a model that's showing us a fraction as being part of a whole. We can also look at fractions on a number line, and in that case we also have to think about what represents a whole. So if we look at the part of the number line between 0 and 1 as representing one whole on our number line, and divide that one whole distance into 3 equal parts, we can say that 2/3 would be 2 of the 3 equal parts between 0 and 1. And another way to represent fractions is with a set model. So to represent 2/3, we could use a set containing 3 objects. And if we show what 2 of those 3 objects look like, then we could say that this represents the fraction 2/3. Now what makes this model a little different is that it's not representing so much part of a whole, it's representing part of a set. The whole in this case would be considered the whole set. Equivalent fractions represent the same number. Now we've talked about the fraction 2/3 and how we can represent it with an area model, so we're going to use that model while we're looking at equivalent fractions. If we take that model and we subdivide it, we take each of the 3 equal pieces and divide them exactly in half, we now have 6 equal pieces in our whole, and 4 of those 6 equal pieces are represented by the shaded part. So we can say that 2/3 is equivalent to 4/6. Now what if we take the same fraction 2/3 and we take this area model, and instead of dividing it up into 2 more equal pieces in the horizontal direction, we divide it into 3 more equal pieces. Now we've got 9 pieces in the whole, And 6 of those 9 equal pieces are represented by the shaded part. So now we have the fraction 6/9, which we can see in the model is equivalent to the fraction 2/3 because the same amount of the fraction is shaded in. Which brings us to something called the fundamental law of fractions. And it's something that you're very familiar with as an adult because you've used it a lot. The fundamental law of fractions says that if we have a fraction and we multiply the numerator and the denominator by the same non-zero value, we will have an equivalent fraction. Now that's really what happened in both of these cases. In the first case, 2/3 equals 4/6, we really multiplied the numerator and denominator of the fraction 2/3 by the number 2. And that's because we took each of the 3 equal pieces and doubled the number of pieces, and we took each of the 2 shaded pieces and doubled them as well. The other thing to notice is this. When we multiply by 2 over 2, we're really multiplying the fraction 2/3 by the number 1. And we know that multiplying a number by 1 does not change the value of the original number because 1 is the multiplicative identity. And in the second case, 2/3 is equal to 6/9 because if we multiply the numerator and the denominator of the fraction by 3, which in essence is multiplying the fraction 2/3 by 3/3 or 1, then we get the fraction 6/9, which is equivalent to 2/3. So how can we show that two fractions are equal to each other? Well, there's several different ways, and the first way we're going to look at is by finding a common denominator between the two fractions. Now we're going to use the fractions 2/3 and 6/9 as our example. The least common denominator of two fractions is the least common multiple of their denominators. If you look at the denominators we have in the two fractions, 3 and 9, the least common multiple of 3 and 9 is 9. So we should be able to write both fractions as having denominators of 9. 2/3 could be rewritten as the equivalent fraction 6/9. And 6/9 obviously already has a denominator of 9. So we've shown that 2/3 is equivalent or equal to 6/9 by writing both fractions with the same denominator. We can also show that two fractions are equal by simplifying both fractions. A fraction is considered to be in simplest form if its numerator and its denominator have no common factor other than 1. Now in the case of 2/3, 2/3 is already simplified because there is no common factor between 2 and 3. 6/9 on the other hand is not simplified because 6 and 9 have a common factor of 3. If we divide the numerator and denominator by 3, we're in essence dividing the fraction by the number 1 because 3/3 is equal to 1, and that doesn't change the value of the fraction. It will, however, change the appearance of the numerator and the denominator so that we now have an equivalent fraction 2/3. So we've shown that 6/9 is equivalent to the fraction 2/3. Now one little note to make about the word simplest form or simplifying fractions. Quite often we learn to use another word that means the same thing to us. Sometimes we learn to use the word reduce when we talk about simplifying fractions. Reduce really is not a good word to use to talk about simplifying fractions because if we said that we were reducing the fraction 6/9, that implies that we're somehow making 6/9 smaller. And we're not making 6/9 smaller when we simplify it. We're simply rewriting it as a fraction that has the same value, but that has different numbers in its numerator and denominator. So if you are used to using the word reduce when you're talking about simplifying fractions, it's a good idea to stop using that word because of what it implies. It's implying that the fractions are becoming smaller when in fact the fraction isn't smaller. It has the same value. Now there's another way to show that two fractions are equal, and that's by doing something called cross multiplying. When we cross multiply, we're using this property of fractions, which says if two fractions are equal, if a over b is equal to c over d, then their cross products are equal. So in this case, a times d equals b times c. We can use that to show that two fractions are or are not equal. So in this case, 2/3 equals 6/9, because 2 times 9, which is 18, and 3 times 6, which is 18, are equal numbers. So the cross products are equal. That's how we can show that two fractions are equal. And likewise, if the cross products were not equal, then we could conclude that the fractions are not equal. So if two fractions aren't equal, then one must be larger than the other, or one must be smaller than the other, which means we can order fractions. We can order rational numbers. When we order rational numbers, we can show which one is larger or smaller by putting a sign in between to show how they compare to each other. So in this case, that's what we're going to do. We're going to either place a less than sign, a greater than sign, or an equal to sign between the two numbers. So let's start with these two. 2/7 and 3/7. If you think about a number line representation for those two numbers, we would have the space on the number line between 0 and 1 divided into 7 equal pieces. And we're comparing 2/7 with 3/7. Well, 3/7 is a larger part of that than 2/7. It's a larger part of the distance between 0 and 1 than 2/7 is. We also can look at the position of the two numbers on the number line, and since 3/7 is to the right of 2/7, it must be larger. So that means 2/7 is smaller than 3/7, and we can put a less than sign in between them. How about 1/5 and -3/5? Now what you'll notice is once again we've got two fractions that have the same denominators. And if the fractions have the same denominators, that means we're comparing fractions that have the same size pieces, in this case fifths. And if that's the case, you can simply compare the numerators to determine which one is larger. Since 1 is greater than -3, 1/5 has to be larger than -3/5. If you think on a number line, a positive number, 1/5, would have to be to the right of the negative number, -3/5, so it must be larger. Now if the denominators aren't the same, it gets a little trickier. So let's think about these two fractions, 1/5 and 1/4, in terms of area models. What we have here is two rectangles, each representing one whole, and you'll notice that the rectangles are the same size. That's important as well. When you're comparing two fractions to determine which one's larger or smaller, you need to make sure that the whole is the same size for both fractions. So for the fraction 1/5, we're dividing the whole into 5 equal pieces, and we're going to be considering one of those pieces. And for the fraction 1/4, we're dividing the whole into 4 equal pieces, and we're considering one of those pieces. It's pretty clear to see that the 1/4 is larger and the 1/5 is smaller. Now if you think about why that must be true, in this case the numerators of the fractions are the same, which means we can look at the denominator to tell us what size the pieces are. And in this case, one piece out of 5 pieces of a whole would have to be smaller than one piece out of 4 pieces of a whole. If we divide the whole up into 4 pieces, those individual pieces would be larger than the fifths that we're dividing the whole into if we divide it into 5 equal pieces. If two fractions are not equal, then we can certainly find something in between them. We can find another rational number in between them. So let's see if we can do that with 1/5 and 1/4. The problem again is that the denominators aren't the same on these fractions. The pieces aren't the same size. So let's rewrite the two fractions so that they have a common denominator. The least common denominator is 20. So if we rewrite the first fraction as 4/20 and the second fraction as 5/20, we can compare them, and we also have a better chance of finding a fraction in between. So we need to think about what would be in between 4/20 and 5/20. And while you might be thinking of 4.5/20, that certainly would be in between 4/20 and 5/20, we need the numerator of the fraction that we're trying to find to be an integer, and 4.5 is not an integer. So we're going to break these pieces up into smaller pieces yet. Right now we have 20ths. What if we break these into 40ths by multiplying numerator and denominator of each fraction by 2? Now we're comparing 8/40ths and 10/40ths. And it's easy to see something that's in between those two. 9/40ths would have to be in between 8/40ths and 10/40ths. Now remember, all we did all the way here down here was to write fractions that were equivalent to our original fractions. So we started with 1/5 and 1/4. Then we had 4/20ths and 5/20ths, and now we have 8/40ths and 10/40ths. And in between those two is the fraction 9/40ths. It's not the only fraction in between 1/5 and 1/4. It's just one that was rather convenient to find. Let's try this again, but now let's look for two rational numbers between the fractions 1/6 and 1/5. Once again, the denominators aren't the same, so if we write these two fractions as equivalent fractions with common denominators, it will be easier to find a fraction in between them. The least common denominator is 30. So if we rewrite the two fractions as 5/30ths and 6/30ths, remember we're looking for two fractions in between 5/30ths and 6/30ths. We don't have any whole numbers between 5 and 6, so we need to divide these fractions a little more. So let's say we divide them, each piece of our fraction, into 60ths. So now 5/30ths is equivalent to 10/60ths, and 6/30ths is the same as 12/60ths. I can see one fraction in between those two pretty clearly. That would be 11/60ths, but I want two that are in between. So let's subdivide again. We're just making the size of the pieces smaller so that we can find a fraction in between these two fractions. So now we have 20/120ths, which is equivalent to our original fraction 1/6, and 24/120ths, which is equivalent to our original fraction 1/5. And now it's pretty easy to see that we've really got lots of fractions that are easy to find between these. 21/120ths, 22/120ths, 23/120ths. We were only asked to find two numbers in between, but now it's pretty clear to see that we can easily find these three. A mixed number represents a sum of an integer and a fraction. 1 1/2 is an example of a mixed number. Implied in a mixed numbers notation is a whole number plus a fraction. So when we see 1 1/2, it really means one whole plus 1/2 of a whole. And if you think about what that would look like if we drew a model for it, it might look something like this. If one whole is considered to be one whole circle, then we could have one whole circle plus half of a circle more. A negative mixed number, like -1 1/2, means -1 plus -1/2. Now that's a little bit tricky to understand. The negative applies to both parts of the mixed number, the whole number part and the fraction. If you think about where these numbers would be on a number line, positive 1 and 1/2 would be halfway between 1 and 2. Negative 1 and 1/2 would be halfway between negative 1 and negative 2. It's negative 1 plus another negative 1/2. Mixed numbers can be changed to improper fractions. An improper fraction has a numerator that's greater than or equal to its denominator. Now if we think about 1 and 2/3, which is a mixed number, that means 1 whole plus 2/3 of a whole. To change this to an improper fraction, we want to take the 1 whole and break it up into 3 equal pieces, just like the 2/3 is broken up into 3 equal pieces. Now we've got 3 out of 3 equal pieces in the 1 whole and 2 out of 3 equal pieces in the 2/3, which means in all we have 5/3. So 5/3, which is an improper fraction, is equal to the mixed number 1 and 2/3. Mixed numbers can also be written if we have an improper fraction. So in this case, we have 5/2 and we want to write that as a mixed number. 5/2 means we have 5 pieces, each the size of 1/2. To write that as a mixed number, we're going to take as many of the pieces of a whole as we can and put them together to make wholes. So in this case, we could put these 2 halves together to make a whole, and these 2 halves together to make a whole, and that still leaves us with a half left. So we have 2 wholes plus 1/2, which is 2 and 1/2. So 5/2, the improper fraction, is equivalent to the mixed number 2 and 1/2. You may recall that there's a way to change an improper fraction to a mixed number if we use division. When we see the fraction 5/2, that really means 5 divided by 2. And when we take 5 and divide it by 2, we get 2 for a quotient that's coming from the 2 wholes. That 2 for a quotient that's the wholes really is coming from 4 halves, and that leaves us with 1/2 remaining. So that 2 remainder 1 means we have 2 wholes plus 1 remaining half, which is our 2 and 1/2. So that's our introduction to rational numbers. The next thing we're going to be doing with rational numbers is looking at how to do the 4 operations with them. So we'll look at adding, subtracting, multiplying, and dividing.